Okay, back again, and we finished up all of our CLEP calculus practice exams downloaded from the internet, and I am going to try to do kind of a review study guide type of thing based on experience of the I think it was 79 questions that we went over, and just the things that you can expect to need to know and deal with. So let's jump into it. Just first of all, algebra. Algebra is the basis for everything that follows it. So you definitely need to be comfortable with manipulating equations, moving things around on the equations, isolating a variable to one side of the equal sign, being able to pull out common factors, fraction stuff. If you have some fraction, and if you can factor out the same thing on the top and the bottom, they can cancel each other out. And if you need to bring something in, you can actually multiply by the same thing on the top and the bottom and bring them in, and sometimes that's useful. Simple fraction rules. If you're multiplying, you just multiply straight across. If you are adding or subtracting, then the denominator on the bottom has to match. Let's see. If you have some function equals whatever, or y equals whatever, and you need to find the x value that makes this equal to 0, be confident in doing that. I should say x value or values, plural. Sometimes there's 2 or even 3. And if y equals a times b, then anything that makes a 0 or b 0 will make the whole thing 0. So if your f of x is, let's say, x minus 3 and x plus 2, then that will be 0 at either x equals 3 or x equals minus 2. So you got to be able be ready to do stuff like that. I think we ran into the Pythagorean theorem once or twice. So right triangle, square of the hypotenuse is equal to the sum of the squares of the other two sides, equals x squared plus y squared. And area of the triangle, 1/2 base times the height. Area of a circle, pi r squared. What else did we get? If you have, exponents. So, we know that x squared is x times x, and x cubed is x times x times x, and x to the first power is just x by itself, as it's times itself only one time. If anything to the 0th power is just 1, it actually does come into play, even though you wouldn't think it would. Anything to a negative power is just the reciprocal to the same power, but positive. And it also works in reverse. If you have a negative exponent on the bottom, you can just bring it up to the top. Anything that is a fractional exponent, that's the same as the square root. Or you might have 1/3, and that's like a cube root. And you can even combine them. I know the one time we had 1/8 to what was, we started with 8 to the negative 2/3, and then we had to take it 1/8 to the positive 2/3, and then it reduced to 1 over 2 squared to get 1 over 4. Because if you have a fractional exponent and it's not a 1 in the numerator, it just works like it ordinarily would. 8 to the 2/3 is the same as cube root of 8 squared, or even the cube root of 8 squared. Works either way. Exponents, and then factoring. One thing that came up several times and is good to keep in mind is when you have a square number minus another square number, you can factor it out real easy to the sum and multiplied by the subtraction. So, for instance, if you have a 5 minus the square root of 7, and we want to get rid of that square root, we can multiply it by 5 plus the square root of 7 and get 25 minus 7. For instance, if this is in the bottom of a fraction, and you multiply the top and bottom by this, so you'd still have that bit up on top of the fraction, but you've gotten rid of the square root from the bottom of the fraction, and that is helpful in a lot of circumstances. Okay, so trigonometry, that's something else that you generally learn before calculus, and it's pretty easy to forget. So we're talking a unit circle with radius 1, and in calculus we always do radians, not degrees. So angles start at 0 at the positive x-axis and then goes counterclockwise. So the negative x direction is pi, which means up there is half pi, and down here is 3/2 pi, and that's also the equivalent to 2 pi. And you have some angle, often designated theta, and that angle, a radius from the unit circle at that angle contacts the circle at a point, which is x and y, and then the sine of that angle is just that y value, radius of 1. The cosine of that angle is equal to the x. The tangent of the angle is the same as the y over the x, or sometimes you might want to call it the sine over the cosine. Same thing. And then you have the inverses of the reciprocals rather. 1 over the sine is the cosecant. 1 over the cosine is the secant. And 1 over the tangent is the cotangent. So, of course, that would be the same thing as 1 over y, 1 over x, and x over y. And let's see, we want to, in trigonometry, you tend to memorize a few key values in here, but across the CLEP exam, it only seemed important to be able to quickly recognize the values at the axes, right? So, this is 1, 0. So the cosine is 1 and the sine is 0. Up here at 0, 1, so the cosine is 0, the sine is 1. Over here at negative 1, 0, the cosine is negative 1, the sine is 0, and then down here at 0, -1, the cosine would be 0, the sine is -1. And if we think about also, if we have that angle, if we reflect that angle across the axis, pardon my drawing for not being perfectly round, this would be the same x and y values numerically, but the x is negative in terms of how it matches up to this. And that angle would be the angle of pi minus theta, because the angle is positive in this direction, so it's from pi minus the angle. And if we were to reflect it down here, that's pi plus theta, and it's, again, those same values, but they're both negative, right? And if we had it over here, it would be 2 pi minus theta, and it's, again, the positive x, but the negative y. So, the signs are all positive up here, and the sign is negative down here, and the cosine is positive over here and negative over here. And then, of course, the tangent is going to be positive up here and down here, because the negatives cancel out, but then the tangent will be negative over here and up here, because one of them is negative and the other is not. And then the only other thing I think that really came up is halfway between 0 and 1/2 pi, you have 1/4 pi, and at that angle, x and y are equal to each other. And if we were in trigonometry, you would generally memorize what that actual value is. But in the question where it came up, we didn't even need to know that. We just needed to know off the top of our heads that it is equal there. The sine and the cosine are equal there. Of course, at the equivalent over here, which would be 3/4 pi, they have the same numerical value, but one is negative, the other is positive. And if you really need to know, I kind of don't expect it to come up, but if you really need to know what that value is, you can use Pythagoras to find it, which is how you originally do that in trigonometry class anyway. But the general trend was only really needing to know the ones and the zeros at the 4-axis point. So I suspect it will stick to that. Okay, and there was also a lot of limit stuff. I was pretty surprised, actually. I remember limits as being the kind of thing that was used to introduce the other topics. How to, the limits were used to derive the main equations that were used, and after that, you kind of looked back and never did anything with limits again. But the practice exams were really heavy on the limit stuff. Really, really interesting. So the limits come at you in a few different ways. One of the main ones is like a gap in a function, right? So if you have some function, but they manipulate it by maybe they do the let's say x minus 2 and x minus 2 on the bottom, and now you have the same function. It looks identical everywhere else except at x equals 2. That makes it divide by 0, which you can't graph, and so it gives you a little graph in a little gap in that graph. And if there's a picture, that's usually depicted by a little circle like that. Or sometimes there's not a picture and you just have to imagine it. And so then usually they would say something like, well, what's the limit as x approaches 2, and you have to figure out, well, what would fill in that gap there, and maybe you factor this out and just remove that to get back to the original, and then you can just plug in x equals 2 and find out what it would be. The other trick they'll do is they'll say, well, you have this, and kind of do a piecemeal function. You have this, and then we'll say separately from that where the function is at x equals 2, then the y value is going to be this. And sometimes what they fill it in with is filling in where it belongs, right in there, and then that makes it continuous again. And sometimes it'll be in the wrong place. It might be up there or something like that, or down there, and you need to recognize that they haven't filled it in properly, that there's a jump there. Let's see, what else did I want to say about the limits? Usually the limit is double-sided, so they want to know what it's doing from both sides. If it's doing something different, if it stops at whatever that value is and then it restarts up there, then it doesn't match, and we have to say the limit doesn't exist unless the limit as x approaches whatever it is, let's say 5. If there's a little minus sign there, they mean the limit only as it's approaching from the negative direction from the left. Or if they put a little plus up there, they mean only as you're approaching from the positive direction from the right. And so in that case, if there's a discontinuity, a jump, it doesn't matter. You just ignore it. You ignore the other half and just look at where it would be if it were reaching that value there. Sometimes we talk about limits. Well, limits almost always occur where there's some kind of, or limit questions about limits almost always occur where there's some kind of problem in the graph, like that, or sometimes it's a vertical asymptote and the graph is going up like that, and maybe it comes back down, maybe it comes back up from the bottom. And so that's the kind of thing where you'd say the limit goes to infinity or negative infinity, as the case may be. Sometimes they're asking, what is the limit as x goes to infinity, or maybe negative infinity? And a lot of the times with that, there's a vertical asymptote, and the graph is approaching that more and more, never touching that. And that's basically just asking, where is that asymptote at? What y value is that asymptote going to be? But occasionally it's just a regular function that goes up and keeps going up more forever, and then as it approaches infinity, it's going, as it goes to infinity in the x direction, it's going to infinity in the y direction as well. So sometimes that's one of those where it's like, well, why did you even ask? Well, because they need to make a math problem, I guess. Let's see. So most of the time you just want to try to figure out what's happening. If it's a gap like that, and you can factor it out to make the gap go away and figure out what that should be, that's great. If it's one of those kind of asymptote situations, what you can do is just plug in, if you're going to infinity, you can imagine just what happens to it if the numbers are very large. If it's something like the limit as x approaches 0, you can think about, well, what's going to happen to this as x gets very small, and just kind of intuit it, just kind of guess from there. If there's an x and an x squared, then for a very small number, x squared is going to get even smaller, even faster than the x by itself will. That kind of thing. And we were given a couple limit problems with trigonometry functions. So again, you just go back to your unit circle. You try to figure out what we're shooting for. what the values are going to be, close to that limit, close to that discontinuity where you can't actually get there, but you can get close and you can imagine what the function is doing near there. And yeah, limits, a lot of the limits, I think they're just when you can't take out a calculator and graph it out or plug a bunch of numbers in and see what it actually does. You just kind of have to, use a little guessing, use a little intuition, and just try to figure out what they're going for. And that's, I guess that's about the best you can do with that. I don't know. Limits are not as tidy, let's just say that, as a lot of other things in math. Okay, the main event with calculus, talking about derivatives and things. The basis of this is, a graph, and you have some function, and you probably remember learning about the slope. So the slope is telling us how fast the graph is increasing. If the graph is just a straight line, we can calculate the slope by picking 2 points and say y2 minus 1 over x2 minus x1, and that gets the slope. And sometimes we might write that as delta y over delta x, delta just meaning the change in, meaning you're subtracting, you're finding the difference between the two, right? And that equals the slope. And if you have a straight line graph, the slope is constant across the entire thing. But if we have something more like a parabola, the slope is not the same. The slope is changing as you go along. And you can draw some tangent lines. Anytime they say tangent, they're talking about the slope, because a tangent line to the curve at the point where it's tangent, the tangent line will have the same slope as the function does at that point. To the left of the point, to the right of the point is going to have a different slope, is going to have a different tangent line, but right there, that the tangent line represents the slope. So if they say tangent, think the slope. If they say, where the two tangent lines are parallel to each other, that means where the two slopes are equal, right? So that's just, they use they choose different words to try to trip you up, and you have to decode what they're saying. So if we have something like a parabola, and we were to calculate the slope at all the different points, and then we took that list of the slope values and we actually put those on a graph too, then that would be the derivative. It is a graph or an equation that describes the slope of the graph that we started with. And what can we learn with that? That's actually, let me redraw this. If we have a parabola, the derivative will be like that. I just did the same thing. I'm terrible. It's going to be like that, because where the derivative is negative, the slope of the original graph is negative, which means as it goes this way, it is going down. And as you go along, the slope is still negative, but it's less negative, so it's going down more slowly. And then as you hit the slope of 0, it's flat. And then when the slope is positive, it's going up. And when it's very positive, it's going up very quickly. And we can also see from this that, being a parabola, we can say there's a minimum of the parabola. This is the lowest value it gets to. It goes down and goes back up. And we can also, that is reflected here, where you can see that the derivative crosses from a negative value to a positive value. And to go from negative to positive, you have to pass 0. So where the derivative is 0, then that represents the minimum. Or if you have a maximum like this, that's the opposite. The slope is positive, and then it hits 0, and then it turns negative. So you have a positive slope, you cross the 0, and you go negative. And then just together, minimums and maximums together are called extrema. So extrema always occur where the slope, where the first derivative is 0, but that's not always the case. It doesn't have to be the case if you have a graph that does something like that. So the slope is 0 here, but there is not a sign change in the slope. The sign is the slope is negative, hits 0, and then goes negative again. So you have, all extrema occur where the slope is 0, but not every slope of 0 is an extrema. So you have to watch for that. And right. So you can repeat that. You can do the same thing if you have the first derivative. You notice the first derivative, the graph of the first derivative also has slope. So if you calculate the slope of every point along there, that gives you some second derivative. And you could keep doing derivatives for as long as you want, but we usually only deal with the first and the second. And again, the second derivative might have negative values, might have positive values, it might cross 0. And what does that tell us about the original graph, right? So if the second derivative is positive, if it's anywhere above the x-axis, then that tells us that the first derivative is increasing, i.e. the slope of the original graph is increasing. So that's something like this, where as you move along, the slope is increasing. The slope is negative, but then it gets less negative, and it turns positive, and then it gets more positive. So that's increasing. And this is known as concave up, where the second derivative is positive. And then if the second derivative is negative, we have the reverse. That means that the slope is decreasing as you go along. The first derivative, the slope is decreasing. And so the original graph, the slope might start high, but as you go along, the slope is getting less and less, might hit 0, and then the slope gets more and more negative. And this would be called concave down. And where the graph changes from concave up to concave down, for instance, something like that, or show it more directly like that, where it changes from concave down to concave up, or from concave up to concave down, that is called an inflection point. And similar to the inflection point on the original graph will be an extrema on the first derivative, and it'll be where it crosses 0 on the second derivative. These things are changing signs. The positive second derivative and the negative second derivative. But again, all inflection points happen where the second derivative is 0, but sometimes where the second derivative is 0 is not an inflection point. So you have to check. So, basically every rule that applies going from the original to the first derivative, same rules apply going from the first derivative to the second derivative. Of course, that's what that means. And you just recognize what either of those things mean about the original graph in terms of increasing, decreasing, minima, maxima, and the inflection points. Okay, real quickly about the notation you'll see. In the older school algebra type stuff, you usually say, y equals something, well, y equals x squared, and then I'd say, where x equals 5, what does y equal? But we also might use a notation like that, and instead of just saying, well, where x equals 5, what does that equal? We just write the 5 inside there and say, what does that equal? And you do it the same way. You just plug in the number into the variable. Under that notation, where f of x is the original function, we put a mark there that represents the first derivative. It looks like an apostrophe, but that's actually called the prime. So it would be, if you were to say this out loud, that would be f prime. And the second derivative is f double prime. And the integral, the opposite of the derivative, in this kind of notation is usually represented as a capital F, right? So if when you go from the derivative to the first derivative, if you want to go backwards from the first derivative to the original, that's called integration. So in this kind of notation, when you can't remove the prime mark when it's not there, so they take the lowercase f and turn it to a capital F. You also might see for the first derivative a ddx or even a dy dx, and that's actually very analogous to that delta y, delta x, d for delta, basically. And so this is just kind of the same way as saying this, but just in calculus, it's more common to use the actual letter d instead of the delta, but that's where that comes from. And then in this kind of notation, the second derivative would be d squared over dx squared, or d squared y over dx squared. So if you see that, that's the second derivative, and that's what that means there. And then if we have some graph, we think of that as the x and the y usually, and some function. And if instead of x, that's time, and instead of y, we call that distance. Now we're measuring how far away something is at any given time. So this is a car driving away, a plane driving away, a train going away, person walking away, whatever it is. And we can do the same things with this. We think about the slope, where the slope is normally the delta y over delta x, but because y is distance and x is time, so what is the change in distance per a change in time? Well, we think of that as just the speed of something, or the velocity. So the first derivative, or the slope, is actually the speed. How fast are you getting further away, right? And then if we were to do the second derivative, now we're thinking about, is the speed changing? Is the slope, like for this one, it's a constant slope, right? But if it was something more like that, the speed is not constant, the speed is increasing. How fast is the speed increasing? That's the second derivative, and that's acceleration. So when you're talking time and distance, the first derivative is your speed or your velocity, and your second derivative is acceleration. And that's that's physics, and that's where what a lot of calculus was, developed to help do that kind of physics stuff. Okay. Let's see how quickly we can pour through the rest of this. Calculating derivatives from an equation. These are the things that you absolutely must remember and be able to do well. So the most common thing you have is we call the power rule. So a times x to some exponent b. To take the derivative of that, we bring the b down, multiply, and then the new exponent is that subtracted. So this works for anything. A could be 1, and then it's just not there. It still works the same. The exponent could be a negative number. The exponent could be a fraction. It still works completely the same as that. Let's see. Right, okay. And then we're going to talk about the product rule. If you have two functions that are multiplied together, and individually you can figure out the derivative of either one individually, but multiplied together it looks like a mess. Then to take the derivative of that, you have to figure out what the two parts are, and the derivative will be the derivative of the one of them. We call it the f times just the original of the other, and then you add that to the original of the first one and the derivative of that. Let's simplify it. Let's get rid of the x's. It's just f prime g plus f g prime. And if it's a division, if you have some function over another function, then that is the quotient rule. And how the quotient rule works is f prime g minus f g prime all over g, the original g, squared. Okay, and then if you have a composite function where one of them is inside another one, and when I mean, when I say inside, that would be something like when you have the cosine of x squared is inside the cosine, or the other way around, cosine of x squared. Now the cosine is inside the squared, right? And both of those are ugly unless you break it into the parts. You consider the cosine and the x squared separately as an f and a g. And when you have this, it's called the chain rule. And so you take the derivative of the outer part, the f part, with the original inner part still as it is, but then multiplied by the derivative of that inner part. And then some other key derivatives that you just have to know off the top of your head. The derivative of the sine is the cosine. Derivative of the cosine is the negative sine. The derivative of the natural log is the natural log of x. All these are x. Kind of implied. The natural log of x is 1 over x, and e to the power of x is its own derivative. It does not change. You can take the derivative. And then, of course, when you are integrating, we're going in reverse. So if you see this, the integral is, again, itself. If you see 1 over x, the integral is the natural log of x. If you see a negative sign, the integral is the cosine. If you see the cosine, the integral is the sine. And, of course, a lot of integrals of the power rule. Again, a to the x, ax to the power b brings you to ab x to the b minus 1. So if you, to go the other way, if we had like a c times x to the power of d, if we want to integrate that, to go from here to here, we subtracted. So back the other way, we have to add. And to get from here to here, we brought that one out in front. So this has to equal something with that brought in. And that original, you would divide this, because c over d plus 1, and you bring the d plus 1 down, and it cancels out, and you're left with the c. So, and just convince yourself that this and this are opposites of each other. If you do this and then do that, you get back to the same place. So, the power rule, real easy, be able to do it in both directions. And then we had a couple of problems where that were actually, they gave us something that was the result of the chain rule and said, find the integral of that, find the antiderivative, do it in reverse. And so a good way to spot that is if you see a function and you see something that you know is the derivative of that function, then that's your g and your g prime. And you can say, okay, if given that, what might have happened, what might the f have been of the original f and the original g in order to reach that. And that's trickier to do, but I think we got 2 of those kinds of problems as we're working through the practice tests. So you might very well expect to see 1 or 2 of those like that on the tests. Maybe also watch out. Maybe you'll see a reverse of a power rule or a quotient rule. But probably there are a lot more use of the chain rule on those practice questions than the product and the quotient rule. But you still definitely remember all 3 of those. And then in a general sense, if you're taking, you have something x squared and something times x and something without an x, that's like an x to the 1, and that's like an x to the 0, right? So when you take the derivative of that, the 0 comes down, and you get 2ax, and you get b, and you get nothing because the 0 comes down and it just goes away. But now if we started with this and they say you need to integrate, well, we don't know what that was. There was some number that got taken away, right? If you have the first derivative, which is the description of the slopes, we can take that description of the slopes and we know what the original graph looked like, what it was shaped like, but we don't know how high or low above the x-axis it is. We don't know where it's situated vertically, right? So when you're taking an integral like that, you just tag on a plus c, and you just say it's some unknown constant. Just to it's implied. We all know it's there, but you have to write it in. Usually if there's multiple choices on it, it's already filled in for all of those. But there was once or twice where that would actually say, okay, so that resultant equation that you got after integrating, here's a point, here's an x value and a y value that is going to be on that equation that you just figured out, and you can take that and plug it in and actually find out what the numerical value of that c is, that constant, and then you can have the whole and proper equation from that. If they give you a value, you can figure that out from that. Okay, and the main thing that you do with an integral is the definite integral. If you're just we're just talking about is the indefinite integral, where you're just finding the equation. But if you do a definite integral, you have some function, whatever, and you want to know the area underneath that function in some bounds. You call it x equals a and x equals b, and that's depicted this way. You have some function, and usually write in dx just to show it's that you have a derivative that you're going to be undoing, right? And so what you do with this, you take the integral of that equation, and you remember what your upper and lower bounds were, and then you plug them in. You take the new function that you found, you plug in the b, and then you subtract the same one with the a plugged in, and you don't have to worry about the c because you're subtracting, the c's cancel out. But you do that, you plug the numbers in, run it through the equation that you found by taking the integral, and that will tell you the area under the curve for that function. And also remember, if you have a function and it crosses the x-axis, right? So because these are negative values down here, that actually counts as negative area, right? If our bounds were a here and b here, and we were to calculate the area of that, it would be completely negative because it's all below. That's negative. And if you happen to have two functions, and they say, well, we want to know what's the area in between those functions, well, you can kind of think of it as they're overlapping, right? So if you take everything that's below the top function and then everything that's below the lower function, and you just subtract, the part below the lower function is just overlapping the first function, and what you really want to know is in here. So if you take the definite integral of the top and subtract the definite integral of the bottom, you're left with the bit that's in between. And so that's how that's done. That's a fairly common thing that calculus tests will ask you to do now and then. I know we definitely saw one or two of those in the practice exams. We also saw some Riemann sums or Riemann sums. I still don't know how it's properly pronounced. And this is another one of those things where I touch on it briefly on the way in, and then never again, because it's a way to estimate. If you haven't learned the definite integral yet, if the definite integral hasn't been invented yet, but you want to do what that does, calculate the area under the graph. So it's the long way to do it. If you have some function and we know some values along that function, we can consider the height of each of those. And if we figure those, so these would be, pardon the drawing, but again, these would be equally spaced, so, that width and that width and that width, they're all equal. And so if you know what the heights of each of these rectangles are, you can add them all together and multiply by the width, and that'll get you, fairly close to what the area underneath that is. And the notation for that, it uses the sigma notation, which denotes the sum. When you want to find the sum of a series of numbers, you use the sigma notation. So usually you have, I equals 1, and then you have some number up on top, which represents the number of different things you're adding together. So in this case, the number of different rectangles, which is, also, you have your upper bound and lower bound, or lower bound and upper bound, and that's divided into, however many rectangles there are. So if it's 50, you're dividing this into 50 equal columns. Right here, that would be 3, so n would be 3. So you have the sigma notation, and then you have your function inside there, and then you're multiplying by whatever the width of the rectangle would be. So that would be the difference between there divided by the number. So if you see sigma notation like this and then some other stuff, that's going to be a Riemann sum, and somewhere in there is going to be a term that represents the width of those rectangles that they're doing. And there's 3 different ways to do a Riemann sum, depending on, you have your point, and you can do a right-handed sum where you're drawing your rectangle out to the right, or you might have a left-handed sum where the point is on the left of the rectangle, or you might be doing a midpoint sum where it's in the middle of the rectangle. And each of these will give you a slightly different end estimate. They're all going to be pretty close to what it really is, but they're each going to be off by a different amount. And so, when you're using Riemann sums to estimate, you kind of try to go, which one is going to get me the closest, and that's just the distinction there. And that's something. There was a question, 2 questions, where the difference came into play because they said, okay, use this specific type of the Riemann sum. And then let's grab this one again. Mean value theorem. So if you have some function and pick any 2 points on the function, they could be like that. It could be a point down here and a point down there. But whatever it is, some function that intersects both of those 2 points, if you calculate the straight line slope between those 2 points, we know for sure that, and the function, as long as it's properly continuous and differentiable, which means that, there's no gaps, there's no jumps, there's no sharp corners, it doesn't do anything weird, it's just a normal function, that it cannot get from here to here without at least one place having a slope that matches that straight line slope. You can't go up and back down without matching the slope there. You can't go down and back up without matching the slope there. If the points are even at the same y value, you can't go up and down or down and up without having at least one place where the slope is the same. And you'd think would be obvious, but they named the whole theorem after it, and there were I think 2 or 3 questions that involved that kind of thing that we found, so it's definitely something to keep in mind. Okay, and then beyond that, there were just a few word problems, kind of, not all of them were word problems even, but just all the, really complex, tricky, looks like a big mess. Usually it gives you a bunch of different information that seems kind of unrelated, and you just kind of got to break it down. You got to say, okay, it's asking me for A. I don't know what A is, but what would I need to figure out what A is? I might need B and C to figure out what A is, and it told me B, right? But I don't know what C is, right? So what do I need to figure out what C is? Well, I'm going to need D and E to figure out what C is, and maybe the problem, it told me what E is, but I don't know what D is. So how do I figure out D? Maybe I need some F and some G, and it told me F and G, right? So now you know where you're going. It gave you F and G, you put those together, you figure out D, you put that with the E you already have, that gets you the C, you put that with the B that you have, and that gets you to the A. So you figure out what you need until you reach the point where you have everything you need, and then you work back, from the inside back to the outside, and just slowly work your way through it, figure out what what you need, how they relate to each other, and the problems are always specifically designed so that you have what you need. You just have to put it together in the right ways to figure out the missing bits that will combine with the other things that you have and get you to the ultimate actual answer that it is asking about. Okay, and then the last thing that is super important, because there's a whole, like third of the test, somewhere between a third and a half of the test, where the calculator is allowed. They're going to give you some problems where you're going to use the calculator. All right, so according to the test, they give you a digital version of the TI-84 Plus, or you might have used an 83 or something like that in school. They're very similar. So does a lot of different stuff, but seem to the questions involving this seem to stick mostly to the graph. So you go to the y equals button that gets you the list, and you can type stuff in. You can do x squared, you can do cosine of x, and so forth. If you happen to want to do a composite function, we have x squared, and then we want to do the cosine of x squared, but instead of typing it out again, we just want to say the cosine of y1, right? So then you can go to the vars menu and arrow over to the y vars and just the function, and then you can fill in the y1, and that would give you the cosine of x squared. Or you could just type it all out again, but maybe the y1 is long and you don't want to have to type it all out again. So the graph function to get you to the graph where that would appear if I left one on there. Trace to put your little cursor on the function, and you can arrow back and forth to see what the values are. Window to fix the dimensions of the graph manually. So the standard is -10 to +10 in either direction, but if we want to see the graph in a tight, if they say oh, we only care about the graph between x equals 1 and x equals 3, so you can put in 1 and 3 so that you can get a direct view right where it's relevant. If you go to the zoom, there's some you can do zoom in and zoom out, and we saw a couple places where zooming in was definitely helpful because it on the wider view there were some important details that were a little lost, but when you zoom in you can see it better. If you do z decimal, that makes it so that each pixel width is 0.1. If you do down here is the integer, that makes it so that each pixel width is just 1, 1.0. And then you can do different things with it. You don't have to, other than the zoom in, you probably don't have to fool around with that too much if you don't want to. It can come in useful at times. Anyway, and the other thing that we use a lot, obviously, the natural log is there, the e to the power of something is there, squared is there. If you need an exponent other than 2, use the caret. X caret 3 is x cubed. There's your trig functions. There's your inverse trig functions if that ever comes up. Signed in -1 means the inverse. You find the angle that gives you some value, right? But the one that came up a lot is the calc menu, and that gives us these options. So for if you have some function graphed, you can find the zero of it. It'll tell you where it crosses the x-axis. If there's a minimum or a maximum, you could ask it to find that for you. If you have two functions and you want to know where they meet, you can pick the intersect, and it'll ask you, pick the first one, pick the second one, and then it'll ask for a guess, and it's just saying put the cursor somewhere close to the cross. Sometimes the functions cross in multiple places, so put the cursor next to the one that you want to know about. And then you have the derivative, and that will find you the numerical derivative at a certain x value that you tell it to, and you can arrow back and forth to get there, or you can just type it in. And then that one is the definite integral. We definitely use that a couple of times, and that will it'll ask you which function, or if you only have one graphed, then I don't think it does, but it'll ask you for the lower bound and the upper bound, and then it'll calculate for you the definite integral there. And I think that was pretty much everything that was important with the calculator. And then beyond that, if you still have, if all of that you got down, and you still have time to maybe try to remember one or two more things, here's some bonus things that definitely turned up on the test, but not very much. So I wouldn't worry. If you're going to prioritize these would be the low priority memorizing things. So one of those that came up a couple of times is exponential growth. So if you have a population of something, a population of bunnies, a population of wolves, whatever, a population of trees in a forest, and they might give you the equation where the change in population, D meaning change, P for population, per given time, DUT meaning the change of time, so the rate of change of population equals some constant K times P representing the current population, right? And if K is positive, the population is increasing. If K is negative, the population is decreasing, at some constant rate. And if you take this and work calculus magic on it, what it turns into is P over P sub 0 e to the power of kt, where t is the amount of time that is passing. P0 is the population at the start of that time. P over here is the population at the end of the time. And you have that E again, and you still have the K. So there are a couple where they said, well, given something like this, what is it going to be over here? And just, even if you can't just, pop this out of your head and write it down like that, you might want to be able to, recognize it, be able to recognize that form. And if they ask you to do any kind of calculations with it, note that you don't necessarily have to know the actual size of the population. If they say the population doubles in t equals 24 hours, you don't really have to know that it went from 50 to 100 or 200 to 400, whatever it is. It's just doubling, so it'll always cancel out to P0 equals 1 and P equals 2. That's doubled. That's all you would need. Because even if it was any other number, it would still just reduce to 1 and 2 because of the doubling, or if it's tripled, then you would say, 1 and 3, or what have you. So that's one of the things that came up. A little more trig stuff. If you think about that unit circle again, where that's x, that's y, x is also cosine, y is also the sine, the hypotenuse is 1, and we, because it is a right triangle, we can also think about Pythagoras, where the square of the hypotenuse equals to the sum of the squares of the other two sides. So 1 squared equals x squared plus y squared. But in terms of trigonometry, x squared is the cosine squared, and y squared is the sine squared. And of course, 1 squared is just 1. So 1 equals the cosine squared plus the sine squared, and that is a thing. When we were talking about derivatives that you have to know, I did not mention the tangent. The derivative of the tangent happens to be the 1 over the cosine squared, or if you really prefer, the secant squared. But that's probably easier to remember. And, remember it if you want to. If you happen to not remember it and you need it, you can also remember that tangent is the sine over the cosine, and use the quotient rule, and then use this fact, and it will take you to this. So if you really need it and you don't remember it, but you remember some other things, then it will get you there. And then the one other thing that we did come across, I think twice, once or twice or 3 times, something like that, were the inverses of the trig functions. And again, what do I mean by inverse? I mean if the sine of theta is some number, let's call it a, then the inverse sine of a equals that theta, or you might see it called the arc sine. That's just different ways of writing the same thing, as we see so often in math. And these are, again, very, very last priority in terms of memorizing things, but the derivative of the arc sine is 1 over the square root of 1 minus x squared, and the derivative of the arc cosine is negative 1 over the square root of 1 minus x squared, and the derivative of the arc tangent is 1 over x, 1 over 1 plus x squared. And those are not easy to remember, I don't think. So I don't blame anybody in not bothering to memorize these. But if you have a chance and decide to go ahead and do that, make an effort to memorize those, then there's probably going to be 1 or 2 questions on the exam where that will come in handy. But again, if all the other things that are said are much more important to know, those will involve many more problems, and not knowing those, if you only miss 1 or 2 questions, but you get the majority of the rest of them correct, then you're going to be set, and that's not going to be a big deal at all. The very last thing that did not come up very much, but came up a little, so it might be worthwhile knowing, is a little logarithm stuff. So the natural log is the inverse of e to the x, and what do I mean by that? Well, if you think about the regular log, which is the log base 10, so if we say, the log of 100 is 2, why? Because 10 to the power of 2 equals 100, right? The log of 1,000 equals 3 because 10 to the 3 equals 1,000. So that works the same way. If you have the natural log of some x equals a, it's because e to the power of that a equals the original number. And so, there wasn't a lot, but kind of thing came up just a little bit. And if you have multiple log things, for instance, if you're adding logs, what that actually becomes is the numbers inside multiplied together. And as you might expect, in terms of subtraction, it works the other way. Right? Minus the log of a equals log of b over a. And, well, why does that work? Well, if you think of let's go back to the base 10. If we're doing the log of 100 or 10,000, which is 5, and the log of 100, which is 2, and the log of 1,000, which is 3, right? So if you have the log of 100 and the log of 1,000, which is 2 plus 3, and you're adding them together, you get 5. And to get from these to there, 100 times 1,000 is the, well, it would be 100,000. So that's why the addition is the multiplication of the inside. Or if you're going in reverse, if you're saying, this minus this, 5 minus 2 equals 3, or this divided by this equals this. So that's why you get this kind of thing. And I didn't see it come up at all, but maybe if you have the log of something added to itself, well, we might be tempted to just say, well, that's 2 times the log of a. But if we think of this rule, it would be multiplying together as log of a squared, and that actually is true either way. So if you had an a squared and you wanted to get rid of it, you just pull out that 2 into the front. And that's just some log stuff. Again, if you don't know any of that, you only miss out on 1 or 2 questions on the exam. But if you happen to remember that, that'll just be those 1 or 2 more questions that you'll be able to get through. But it's not a main feature of calculus. It's not a main feature of that stuff on the test. So that's low priority in terms of memorization. And that basically sums up everything that we ran into running through those practice problems. So I will conclude there, and good luck on the exam.